Welcome back to our discussion of the flow in a pipe, our discussion of momentum transport as part of the course on fundamentals of transport processes. The last class we were looking at the flow in a pipe. This is a flow that is used often, and in this case the surface is a cylindrical surface, a curved surface, and therefore it is appropriate to use a cylindrical coordinate system for analyzing the flow in a pipe. So, we consider a pipe of radius r across which there was a pressure difference that was applied, okay, and that difference in pressure was responsible for generating a flow in this pipe. This pressure difference of course has no real analog in mass and heat transfer. So, it is specific to momentum transfer. Okay. We have done the balance equations between a surface at r and a surface at r plus delta r. We had written that the rate of change of momentum is equal to the sum of the applied forces. Okay. This momentum balance equation was done for the x direction, the x momentum, the streamwise momentum. Okay. So, in that case we had written that the rate of change of momentum between two instants of time separated by delta t, which is basically the difference in momentum density times the volume, is equal to the forces. There are forces exerted at this outer surface at r plus delta r, the inner surface at r, okay, as well as the end caps, the surfaces at x and x plus delta x. At these surfaces there is of course a flux of momentum coming in and a flux of momentum going out. Okay. So, there is momentum coming in through the surface because the fluid velocity is along the x direction. There is momentum leaving the surface as well on the right side because the velocity is in the x direction. In addition to that, there is a pressure force. Okay. Pressure, as I had told you in the last class, is compressive. It always acts inward to the surface. Okay. The pressure is always acting inward to any surface. Okay. So, it acts along the inward unit normal to the surface, the inward perpendicular to the surface. Therefore, the pressure at these two end surfaces is what enters into the x momentum balance equation. The pressure at the curved surfaces is not in the x direction. Okay. The pressure at the curved surfaces is not in the x direction. So, therefore, this pressure does not enter into the momentum balance equation. Okay. What enters into the momentum balance equation is the shear stress in the x direction, which actually acts parallel to the surface. Okay. The shear stress acts parallel to the surface. So, this is what enters into the x momentum balance equation. However, at the two end surfaces the pressure is perpendicular to the surface and it is in the x direction. So, that pressure enters into the x momentum balance equation. So, these were the two forces exerted, the first set at the surface at r and r plus delta r, the second set at the surfaces at x and x plus delta x, the two end surfaces. Okay. So, once we have written these momentum balance equations correctly, it is only a matter of dividing by volume and taking the limit. Okay. And we end up with this momentum balance equation. This contains a shear stress term. Okay. This is slightly complicated because for the curved surfaces the surface area changes as the radius changes, and this factor of r actually takes that into account, because the surface area is proportional to the perimeter, which is proportional to the radius. So, that is the additional term due to the momentum, due to the curvilinear coordinate system, and then I have a pressure gradient here, a derivative of pressure with respect to the x direction. Okay. And this appears because the pressure at the two end caps is different. The pressure at x and x plus delta x have to be different because that is what is driving the flow. So, I had written that momentum balance equation here and then written down Newton's law for viscosity and got a balance equation for the x momentum. Okay. So, let me write that once again for you. The total momentum conservation equation for a general unsteady flow, okay, for a general unsteady flow has to be of the form mu by r d by dr of r dux by dr, okay, minus dp by dx. Okay. So, that is the momentum balance equation. Okay. First we consider and the boundary conditions, okay, at the surface of the pipe r is equal to r, ux is equal to 0, and at r is equal to 0, as I had explained in the previous class, we have the symmetry condition partial ux by partial r is equal to 0. Okay. Okay, so, those are the boundary conditions. And now we have to solve this. First, of course, we will take the steady solution. Okay. The steady solution, the time derivative is 0. So, I just get mu by r d by dr of r partial ux by partial r is equal to dp by dx. Okay. Okay, so, that is the equation at steady state. Okay. The left side of this equation is equal to 0 because there is no time dependence. Okay. And now you can solve this. Okay. You will get, okay, first you will get d by dr of r partial ux by partial r is equal to r by mu dp by dx. As I told you, the pressure gradient had to be a constant. Okay, it is independent of the x direction. Okay. The pressure gradient is independent of the x direction. Okay. The pressure is also independent of the radial coordinate. Okay. So, this is once again something that is not easily appreciated. Okay. Let me just briefly tell you why. Okay. The momentum balance that I have written here is for the x momentum, okay, the momentum along the flow. Okay. I could write a momentum balance equation perpendicular to the flow, okay, in the radial direction, okay, in any direction that is perpendicular to the flow. Okay. For any direction perpendicular to the flow, the velocity is equal to 0. Okay. For any direction that is perpendicular to the flow, the velocity is equal to 0 because the velocity is only in the x direction. Okay. So, if I were to write a momentum balance equation for any direction that is perpendicular to the flow, okay, the velocities are all 0, that is the equivalence of all of these terms, the equivalence of these terms, and the shear stresses, they are all 0 because the velocity is 0. Okay. So, in any direction that is perpendicular to the flow, I will be left only with this pressure term. Okay. In any direction that is perpendicular to the flow, I will get an equation of this form except that all the velocities are 0, okay, because the velocity is only in the x direction. Therefore, I will get only a pressure gradient in that direction is equal to 0. Okay. So, therefore, the pressure has to be a constant in any cross section perpendicular to the flow. That is because there is nothing to balance that pressure gradient. Okay. There is no viscous stress or inertial stress to balance that pressure gradient perpendicular to the flow because the velocity is identically 0 perpendicular to the flow. Okay. And for that reason, the pressure has to be a constant across the cross section. Okay. So, therefore, the pressure gradient is also independent of the radial coordinate. Therefore, I can integrate it. Okay. Integrate it once and you will get r partial ux by partial r is equal to r square by 2 mu partial p by partial x plus some constant C1. Okay. Simplify, partial ux by partial r is equal to r by 2 mu partial p by partial x plus C1 by r, and integrate it once more and you will get ux is equal to r square by 4 mu partial p by partial x plus C1 log r plus C2. Okay. So, for this steady equation, the steady solution is ux is equal to r square by 4 mu partial p by partial x plus C1 log r plus C2. and the constants C 1 and C 2 have to be determined from the boundary conditions. Okay. We know that at the center dux by dr is equal to 0. At the center dux by dr is equal to 0. That will be true only if C 1 is equal to 0. Okay. At the center dux by dr is equal to 0, that will be true only if C 1 is equal to 0, right. Therefore, this logarithmic term has to be equal to 0, because log of r in the limit as r goes to 0 goes to infinity. So, therefore, this velocity profile, if C 1 is non-zero, does not satisfy the condition that the velocity has to be finite at the center. Okay. C 2 can be determined from the other boundary condition. Okay. At r is equal to capital R, the velocity is equal to 0. Okay. And the velocity profile that satisfies both of these conditions is ux is equal to minus 1 by 4 mu partial p by partial x into r square minus r square. Okay. So, that is the velocity profile, okay, which satisfies both the boundary conditions and satisfies the momentum balance condition. Okay. Therefore, my velocity ux is equal to, I can rewrite it slightly as r square by 4 mu partial p by partial x into 1 minus r by r the whole square. Okay. So, that is the velocity profile. Okay. Note that ux is positive if dp by dx is negative. Okay. Basically, if the pressure at the inlet is greater than the pressure at the outlet, the pressure gradient is negative. Okay. If the pressure at the inlet is greater than the pressure at the outlet, the pressure gradient is negative. Okay. Therefore, ux is positive. So, the flow is from region of high pressure to a region of low pressure, okay. And that is the reason for this negative sign here. Okay. That is the reason for this negative sign here. Okay. The velocity profile is parabolic in the radius. Okay. So, this is the reason that the velocity profile in the flow through a pipe is a parabolic velocity profile. Okay. At steady state, you get a parabolic velocity profile, okay, with a maximum at the center. Okay. This is for a laminar flow. Okay. It is a maximum at the center. The velocity profile is a parabolic velocity profile. Okay. Now, you can calculate the shear stress tau x r is equal to mu times partial ux by partial r. Okay. Okay. Should be equal to minus partial p by partial x into r by 2 mu, okay, if I take the derivative. Okay. Okay. I am sorry, I should have a positive sign here. Okay. So, let us just work it out a little bit. Okay. So, partial ux by partial r is equal to minus r square by 4 mu dp by dx into minus 2 r by r square. Okay. If I take the derivative of this term here. Okay. If I take the derivative of this term, okay, I will get minus 2r by r square. Okay. So, that is the shear stress, okay, and these two will cancel out, okay, to give me plus dp by dx, and this 4 and 2 will cancel out to give me a 2 here. Okay. So, that is the expression for the shear stress. Shear stress is 0 at the center, okay, because the slope of the velocity is equal to 0. Okay. However, it is non-zero at the wall. Okay. It is non-zero at the wall. Okay. At the wall of the pipe, the shear stress, okay, tau w is equal to dp by dx into r by 2 mu. Okay. I'm sorry, there should be no viscosity there, okay, because I multiplied by this viscosity here. Okay. When I multiply by this viscosity, I don't get a factor of the viscosity there. Okay. Okay, so that is the wall shear stress, okay, exerted on the wall of the pipe. Okay. One can now calculate the average velocity. Okay, one can now calculate the average velocity. Okay. The total flow rate, okay, Q is equal to integral, okay, 2 pi r dr, okay, from 0 to r times ux. Okay. So, how do I calculate the flow rate? So, if I have a pipe of radius r, right, I take a differential element, okay, between r and r plus delta r, okay, differential element between r and r plus delta r. The velocity ux is only a function of the radius. Okay. So, therefore, I have to take the velocity and multiply it by the surface area to get the flow rate, the amount flowing per unit time. Okay. I have to take the velocity and multiply it by the area, okay, the cross sectional area here, okay, to find out the total amount that is crossing one particular cross section per unit time. Okay. You can see that the velocity times the area has dimensions of volume per unit time. Okay. So, there is a flow rate. Okay. So, I take the velocity at one particular radius, okay, multiplied by the area, which is 2 pi r times delta r. Okay. The area is equal to the thickness of this slice times the perimeter. So, it is 2 pi r times delta r, and I have to integrate it from 0 to r. Okay. So, that gives me the total flow rate. Okay. So, this will be equal to minus r square by 4 mu delta p by delta x integral 0 to r, okay, of dr into r into 1 minus r by r the whole square, okay, and I have an additional factor of 2 pi here. Okay. 2 pi is just a constant. Okay. So, I have integral of r square minus r, I am sorry, integral of r minus r to the 4. Okay. So, this will be equal to minus r square by 4 mu dp by dx times 2 pi into r square by 2 minus r power 4 by 4 r square between 0 and r. Okay. So, that is what I get by doing the integral. Okay. So, this gives me minus 2 pi r square by 4 mu, okay, into dp by dx. Okay. At 0, both of these terms are 0. At capital R, I just have to substitute capital R here. Okay. So, I will basically get r square by 2 by 4, I am sorry. Okay, 1 by 2 minus 1 by 4, it just gives me 1 by 4. Okay. So, that is the flow rate. Okay. That is the flow rate in this pipe. Okay. Volume transferred per unit area per unit time. Okay. And the average velocity u bar, the average velocity is equal to the flow rate divided by the cross sectional area, okay, is equal to q by pi r square. Okay. The average velocity is just the ratio of the flow rate and the cross sectional area. Okay. So, if I do that, okay, the pi's will cancel out and I will get minus partial p by partial x, okay, into r square by 8 mu. Okay. Okay. Because this one factor of r square cancels out with this denominator, okay, and I will just get minus partial p by partial x into r square by 8 mu. So, that is the mean velocity. Okay. So, therefore, the mean velocity u x bar is equal to minus partial p by partial x into r square by 8 mu. Okay. What is the maximum velocity? Okay, the maximum velocity is the velocity when r is equal to 0, because the velocity has a maximum at the center of the pipe. So, the maximum velocity is the velocity at r is equal to 0. Okay. I just use u bar for the mean velocity. The maximum velocity is just the velocity if I substitute r is equal to 0 in this expression. If I substitute r is equal to 0 here, I will get the maximum velocity. Okay. So, this maximum velocity is equal to minus r square by 4 mu, okay, partial p by partial x, okay, which is just equal to 2 times the mean velocity. Okay. So, the maximum velocity at the center of the channel is just equal to 2 times the mean velocity, okay, in this particular pipe flow. So, now that we have the flow rate, the mean velocity as well as the shear stress, we can now calculate what is the friction factor for a pipe flow. Okay. The friction factor, okay, is equal to tau w by half rho u bar square. Okay, that is how it is defined. Okay. The friction factor is the wall shear stress divided by half rho u bar square. Okay. Now, we know that tau w is equal to partial p by partial x into r by 2, okay, divided by half rho. Okay. Rather than writing u bar square in terms of this factor here, you will see that for it will be convenient for us to write this as u bar times minus partial p by partial x r square by 8 mu. Okay. So, I am just writing this in this form just for convenience. One u bar I have expanded out and the other u bar I have just retained, okay, as a constant. Okay. So, here this pressure gradient cancels out, okay, and one factor of r will cancel out. Okay. So, I will get mu by rho u bar r times a factor. Okay. This 1 over 2 will cancel out and I have 1 over 8. So, I will just have a factor of 8 here. Okay. If I simplify this expression, you can see that this factor of 8 is there, the factor of 2 cancels out in the numerator and the denominator. Okay. So, 8 mu by rho u bar r. Okay. If I write the radius, okay, is equal to 1/2 the diameter of the pipe, okay, then in terms of this, the friction factor is equal to 16 mu by rho u bar d, okay, which is equal to 16 by the Reynolds number. Okay. So, this is the friction factor versus Reynolds number correlation, okay, for the flow in a pipe. Okay. The friction factor was defined as the wall shear stress scaled by the inertial scales. Okay. I told you in the very first lecture that whenever we define friction factor, it is scaled by the inertial scales. Okay. Therefore, we had defined the friction factor as the wall shear stress divided by the inertial scales. We had calculated explicitly what is the velocity profile everywhere in the flow. We had calculated what is the wall shear stress, and from that we had written down the friction factor as the ratio of the wall shear stress divided by half rho u square, and once I did that, I got the friction factor entirely in terms of the Reynolds number for a laminar flow. Okay. And that expression is the expression, the standard expression for friction factor in a pipe. Friction factor is equal to 16 by Reynolds number, where the Reynolds number was defined as rho u bar d by mu. It could be defined in terms of the mean velocity and the diameter. Okay. Another way to define it is in terms of the maximum velocity and the radius. Okay. For a pipe flow, these two definitions are the same, okay, because the diameter is 2 times the radius, the mean velocity is 1/2 of the maximum velocity. Okay. So, for the particular case of a pipe flow, these two definitions of the Reynolds number coincide. Okay. It does not happen for other geometries. In the case of the flow in a channel, for example, these two definitions will not in general coincide. For the particular case of a pipe flow, these two definitions coincide. Okay. And therefore, for a pipe flow, okay, we have got the velocity profile, the friction factor, and if I plot log of friction factor versus log of Reynolds number, okay, it has a -1 slope in a log-log graph, and this one is 16 by Re, okay, for a pipe flow. Okay. So, this is all for what is called a laminar flow. Okay. This is all for what is called a laminar flow, okay, where the velocity profile in the pipe consists of nice smooth streamlines. Okay. Okay. The velocity profile is parabolic, okay, and the fluid motion is along straight streamlines, and momentum diffusion across the streamlines can take place only due to, momentum transport across the streamlines can take place only due to momentum diffusion. Okay. So, this is the special case of a pipe flow for a laminar flow, and we know that a laminar flow, the Reynolds number up to about 2100, the flow in a pipe is laminar. At some point there is a transition to a turbulent flow, and that point you get different, okay, result for the friction factor as a function of Reynolds number, a result that could in general depend upon the roughness of the wall of the pipe. Okay. So, I have got you the relation only for a laminar flow from momentum balances. For a pressure gradient, the parabolic velocity profile across the pipe, okay, the details of the velocity profile as a function of the pressure gradient, the shear stress, the wall shear stress, the average flow rate, the mean velocity, and from the shear stress and the mean velocity expressions, we can get an expression for the friction factor. Okay. All of this is for laminar flow. I will continue a little bit on pipe flow, looking a little deeper at what happens after the transition to turbulence. There I will not be able to do an exact calculation for you, but I will try to give you some idea of how a turbulent flow is different from a laminar flow, a qualitative picture, and after that we will look at unsteady flows. So, we will continue this discussion of pipe flows in the next lecture. I will see you then.